The Fourier transform is used in a variety of contexts. In this class, we really only are introducing some of the very basics about it. It is used in a lot of places. For example, in signal processing, if you get a signal, like an audio signal, maybe you'd like to decompose that signal into its different frequencies, the frequency spectrum. You can do that using the Fourier transform. If you think about the Fourier transform as giving you the coefficients in the Fourier series of your function. However, since this entire quarter we've been solving differential equations and partial differential equations, I thought it'd be nice to end with an example showing how the Fourier transform can be used to solve a heat equation. So consider the heat equation given by the partial derivative of u with respect to t is equal to some constant, k, positive constant, times the second partial with respect to x. This is the heat equation, and I'm not going to specify that there's any endpoints. So you can imagine this modeling the heat diffusion in an infinitely long metal rod. So this is a heat in a metal rod that's very long, infinitely long, let's say. And I'm going to give an initial condition. So I'm going to say at time 0 and at location x, we're struck by the Dirac delta function, meaning that maybe this is a rod that's struck by lightning at time 0, so instant hit by the Dirac delta function. We can solve this system using the Fourier transform. So watch this. Here's my solution. I'm going to start in the same way that we were solving differential equations with the Laplace transform. I'm going to start with just applying the Fourier transform everywhere. So apply the Fourier transform, and if I do that to the top row of the system, I should remark, I'm going to apply the Fourier transform with respect to the x variable. So we define the Fourier transform as applying on the t variable, but of course I could apply on the x variable as well. So I'm going to apply on the x variable, meaning that I'm just going to write down the Fourier transform of the partial ut tx here. However, since I'm applying the Fourier transform on the x variable, and since the Fourier transform is linear, meaning I could factor out the constant k, this second part is the second derivative. And as we saw on the previous video, the second derivative gives me a term of the form negative omega squared times the Fourier transform of my function. So what I'm saying here is that I'm using the property that the Fourier transform of a derivative, like f prime of x, is I omega times the Fourier transform of f of x. Okay, well that's the first row. That's the Fourier transform of my partial differential equation. The Fourier transform of the next row, that'd be the Fourier transform of this initial condition. This will be the Fourier transform of the Dirac delta function. And since we already know the Laplace transform of the Dirac delta function, I'll use that property on the previous page that said this is 1 over 2 pi times the Laplace transform of the Dirac delta function, except I'm going to replace every s in the Laplace transform with I omega. So the Laplace transform of the Dirac delta function is 1 over 2 pi times e to the negative 0s, and I'm going to replace that s with I omega. So I really just get 1 over 2 pi. Okay, well now I have an ordinary differential equation in t. So if I consider, if I let y equal the Fourier transform of this function, this new function is really a function in t and omega. So I changed all the x's into omegas using the Fourier transform. So we really have the differential equation that the derivative of y with respect to t is equal to negative k omega squared y. This is the derivative with respect to t. And now I have a pretty easy differential equation to solve. This one you could solve almost by inspection. So therefore, my function is equal to some constant that could involve x or omega. So I'll write x or omega there. It's just some constant. Times e to the negative k omega squared t. So I solved this differential equation in the t variable. Now we have an initial condition. So if I plug in times 0, I should get out 1 over 2 pi. So using that, the initial condition is 1 over 2 pi, we finally find the constant in front, because if I stick in 0 for t here, I get e to the 0, which is 1. We find that my function has Fourier transform given by 1 over 2 pi e to the negative k omega squared t. All right. Now I'd like to undo the Fourier transform. And the key to undoing the Fourier transform lies in the Fourier relations. That's what kind of undoes the Fourier transform for us. So using the Fourier relations, I think we find that the actual function we've been looking for is the integral from negative infinity to infinity of this Fourier transform times e to the positive I omega x, and that's an integral with respect to omega. I could plug in explicitly what I know, and I get 1 over 2 pi e to the negative k omega squared t times e to the I omega x, and then I can integrate with respect to omega. Now this is an integral of something that's kind of the form e to the x squared, so I'm not going to do all the simplification steps for you. I think I actually asked you to do integrals of this type on the very first homework assignment, but I'm going to employ the well-known integral, that the integral from negative infinity to infinity of something of the form e to the negative omega squared d omega turns out to be 1 over the square root of pi. So I could do that along with a u sub. I don't know, I'm not going to show you the details, but I am going to show you the final answer, which is 1 over the square root of, or 1 over 2 times the square root of pi kt times e to the negative x squared divided by 4kt. So that is the final answer to this heat equation problem. So what was the overall strategy that we employed? Well, I took the Fourier transform of everything. I used properties of the Fourier transform, in particular, how to take the Fourier transform of derivatives to simplify. Then I got an answer which I could then solve. Then I got a differential equation in t. I could solve that. I get my Fourier transform. And then to undo the Fourier transform, I employ the Fourier relations and find my actual answer. All right, wonderful.